I think we'll kick things off with Sanjay Kudale. He's going to talk about PICO. So yeah, take it away, Sanjay. I'll give you a 5-minute warning, okay?
Yeah. All right. Yeah, thank you, sir. Good morning, all. So you listen to morning talks and everybody talks about this starting the telescope, commensal operation, and then coming to the data and looking for the parallel beam in the time domain and then generating the trigger. So what next? So I'm going to talk about the what next we are going to do. That's filling the gap between the detection and the end users. Okay, the talk is about the prompt imaging of the cosmic burst. We call it a PICO. It's a real-time localization pipeline for the Spotlight. And I'm Sanjay talking on behalf of the Spotlight team. And other team members are Arpan, Jairam, Harshvardhan, Jayanta, and there are many more, of course, and Raghav, of course. A quick introduction. So FRBs are something like a bright millisecond duration radio pulses from the extragalactic origins. They have extremely high energy, about 10 to the power 32 to 48x, released in a very short duration. And the dispersion measures are they're very huge, about few hundreds of the past per cc. That indicates the cosmological origins. And there are two population known, repeating and apparently non-repeating. The flash once they go off, and the repeating they generally comes back in a certain activity period. And the first discovered is a Lorimer burst in 2007, and there are many thousands are detected. There are key observational properties like a durations up to 0.1 to 100 milliseconds sort of, and they are highly polarized and they show some complex temporal and the spectral structures. So what do you post detection? The most important to follow in the science is actually probing the host galaxies, their local environment and everything. There are plenty of stuff to be done. So what is the process actually? We do the detection first, then we have to do a radio imaging, the local interferometer, then as a follow further for highly precise localization, we go to the VLBI. So what I'm going to talk about is the center part, the radio imaging with the local interferometer. Now to mention this, to study this about the studies, we need to know the exact location of the FRB in the sky. Now, though the survey instrument in the common, they are very good in the extreme field of view, helpful in detecting thousands of FRBs. The resolution is not sufficient most of the time to associate the burst to the host galaxies. And that's the bottleneck for other telescopes. So on the other hand, the radio interferometer do not have the large FOV, but have excellent resolution to comparison. To compensate, and the repeater can be followed up, but not repeater rely only the detection in the real-time instrumentation. That's where the imaging pipeline plays very good role in. And as activity varies in the research varies, and to detect the rapid multi-wavelength counterpart, rapid localization is essential. What's Spotlight about? I'll give a 1 minute on the introduction. The Spotlight is a petabyte commensal backend at JMRT. Main focus specifically on the Spotlight's capability to provide the real-time arc-second localization. And it has a frequency coverage from 300 to 1460 megahertz with the fluence limit of 0.2 Jansky millisecond, and accessing the very low energy burst that remains uncharted for the other telescopes. With the largest baseline about 25 kilometers, we can localize the FRB with the arc-second precision, compensating for the modest field of view for the exceptional frequency coverage and the sensitivity and the resolution. The multi-beam capabilities of the Spotlight first localize the burst at the arc-minute precision. Earlier speaker did not mention that, but I would like to say that when the time beam, the search is happened, we are forming the multiple beam using the post-correlation beamformer, where we are using the moderate array antennas. Instead of all 30 antenna from JMRT, we use something like 20 to 23 antenna. That makes the field of view slightly broader, and that covers larger field of view, but that limits the sensitivity, and that gives you actually arc-minute precision. But the imaging pipeline, actually, we record the full visibility and go for the full resolution imaging. That is called the refined arc-second precision. And the real-time imaging it is very super valuable for the rapid external triggers and alerts. This block diagram you already seen. There's a control, then the beam tiling and the control correlator and the beamformer. And in real time, we are looking for the transient search, which about Kshitija and Ujjwala's talk about. When there is a trigger generated by automatic AI tools, the trigger generate controller actually read the trigger through the classifier log, and it generates the triggering, the dumping the beamform data plus the raw voltage, baseband voltages, and the visibility data, along with all the required information that we call the metadata, like a frequency information, the burst duration, burst time, and the dispersion of the burst, DM of the burst. And after having that recorded, we trigger the real-time imaging pipeline, and this is what I'm going to talk about. After this real-time imaging, they produce the images that is given to the discovery database, and someone select that is a genuine detection, and that is given to the next processing of the baseband voltages in the offline. Okay, Spotlight, the imaging methodology. The Spotlight operates using the post-correlation beams. Everything is a post-correlation here, which are the most sensitive and the RFI resistance than the traditional approaches. Traditional approaches with we operate in the phased array. Phased array generally have the IA component. It's a power component that carries all the RFI, the receiver instability in each of the beams. So we reduce that actually. So Roy et al. Have done great work to demonstrate how the post-correlation beams and the PI beams are actually different. In the post-correlation beam, actually your signal also drop down, but amount of the instability, RFI or whatever receiver instability goes down, you get a very substantial boost in the sensitivity. So post-correlation beam is formed directly from the real-time calibrated visibility. So one part of the this spotlight, one feature is very important in this case, although it's conventional, GMRT generally observe like a plane, like a calibrator, then target, then calibrator, and they do offline calibration. But in this case, actually, whenever we point our telescope to the calibrator, we generally carry a phasing of the calibration of the system, and that calibrate all the visibilities we recorded during the burst or during that scan, they are already calibrated. And that always runs in the conventional mode. We do not have to do anything. That's automatically happening. And critically, this means always 1.3 milliseconds, the fast visibilities are always available in the system. And upon detection, these visibilities are immediately dumped to the dumped for the burst duration, and the imaging pipeline is immediately triggered. And the availability of the pre-computed 1.3 millisecond visibility saves us from the extremely computational offline analysis, because that will take huge amount of time and there will be a delay in the follow-up. So 1.3 is actually existing data in the buffer that we record and carry the imaging immediately. That saves the time. And the architecture enables real-time localization with the minimal computational overlay, a key advantage for the rapid follow-up with the multiple systems. So PICO pipeline, the methodology. So real-time imaging, PICO is called a prompt imaging. As I said, prompt imaging of the cosmic outburst, that's our name. So post-detection triggers visibility and the voltage of data dumping along with the metadata. For more details on the voltage dumps and the offline analysis, Chahat will be talking about. Now, after this step, PICO will do, the details are there. The data structure, what we do here. When the trigger is generated, the spotlight correlate dump the visibility as in a 16 time slice manner. So each slice goes in the individual node. That's how the data is sampled and actually processed in the individual node that Harshvardhan has mentioned in the morning. And that covers one block of 1.4 second. That 1.4 second get divided into the 16 time slice. And they are actually accurately timestamped, and the data format is 16-bit half float data. And data specification is actually, it requires always a 4K channels, 1.3 time resolution with the 2 polarization channel and all baseline 435 in case of GMRT. So main software components, when detection triggers the PICO pipeline, the pipeline has 3 functional models. The one is the top level script that does actually it's a main script that reads the configuration file, the data, and it generates the job. That job it keeps ready in some database. And the second one is actually the compute engine. That script reads the job list, jobs file, and fires one that carries the imaging. And the third one is actually a monitoring. It looks for all the clusters. It's a sub cluster of the 8 compute node. It keeps track of the where is what running and keep managing all the imaging one. So what imaging does? There are 3 blocks actually. That's a fundamental. First thing, the raw data that is generated by a trigger recording 1.3 millisecond visibility, that is converted to the raw or to the feeds conversion, and then feeds is converted to the measurement set in the CASA and then carried in imaging. Now each process has its own computational weight, and the monitor script update the status. This update the status file, that information of all the available servers within the imaging subcluster. This keeps a track of what loads is happening everywhere across the clusters. And based on the computational weight, the monitor script submit the jobs to the least loaded server. So it keeps dynamically changing. And of course, this script actually keeps watching whether a finished job and of course date job, they get stuck or something. They try to clear up every year periodically. The step 1, pre-processing a PICO. PICO relies on the detection pipeline, of course, the burst arrival time and the burst duration and the DM. These 3 are key parameters that comes from the detection pipeline. The first step of the PICO PICO pipeline involves converting the binary data to the global feeds format. These steps we use our home written software for the GMRT, the feeds file conversion, and then PICO first find the burst location. I'll show you one graph here in the next clip. We find the location that's coming along with the metadata, and then follows the burst trail. It models the DM from the starting time to the given the dispersion where the burst my burst would dispersion. It put the model line there as a like a border line, and within that trail only it select the visibility that falls in that available, which is the time in that frame, time and the frequency where the burst is alive. Only that data has been selected for the imaging. That is what we are carrying the effectively dispersion. Now a reference channel is chosen and all UV coordinates are scaled to the wavelength of the frequency, reference frequency, and this creates a single fits file, and the UV points are for all the UV points on the MFS grid. Okay. So bandpass calibration and RFI flagging. So JMRT has a slightly slopy band shape. So there it can introduce the weighting issues in the imaging steps, and hence using off-pulse region, we separately normalize the two polarization channels. Normalization, we do a scaling or amplitude scaling is a kind of the bandpass calibration, amplitude calibration. That will take effectively a frequency variation of the instrumental gain, and the MAD-based flagging algorithm is implemented to detect and the flag a strong RFI and the visibility outliers across the channels. The flagging is done via simple threshold-based masking during the data conversion, focusing on the removal of the obvious outliers only, very obvious. It doesn't go for a very deep cleaning. And bad antennas are skipped during the conversion. We converge from the GMRT raw data to feeds file. Bad antennas are essentially removed at that location, and that bad antenna list you get it from the phasing skip. When phasing carries out the operation, it knows what are the antenna. They get the bad solution immediately. It make the list. That list is provided to this one, and so that no bad antenna is going into the imaging here onwards. And the feeds file are handed to the CASA for conversion to measurement set for imaging. So we have demonstrated in-field phasing. Of course, the other point actually, we have demonstrated in-field phasing. There's a poster outside that on the target field, given the model of the field, you can solve for the gain, antenna-based gain. Yeah, sorry. And the gain, and you can immediately load it, but that is useful for the offline analysis. This is how my pulse looks like. This is my raw pulse, single pulse. And this is actually the model dispersion curve. We select the only visibility between these 2 points. And the second plot says the RFI and there's a structure in the bandpass, they are removed. That's much more cleaner here. And then imaging actually, so we run the imaging with the WS screen. For the basic Fourier inversion using the small number of iterations, about 100 or 200, and the image size of the full field of view of the GMRT for the detection at the detection frequency. We do not do much cleaning here, but we get our aim is to get the burst array deck and with the short span of the data. Most of the other continuum sources are not detected there, just because we are selecting only these visibilities. And we typically image up to the half power of the GMRT primary beam. And we have tested imaging pipeline extensively on the pulsar field so far. And recently to validate the pipeline working, we tested the putting the pulsar off field also, of course, and we see whether the pulsar in the image plane is appearing at the place of the it's a coordinate. And this is my image. It shows it's a very nicely detected pulsar here. And this is what in the time domain we see 155 sigma detection. In the image domain we see the 150 sigma detection. This could still improve with self-calibration. And the coordinates we obtain from the spotlight and the 18F, they are very, very well matching with each other. And to process single trigger, we typically use 30 to 64 gigabytes of memory and the 16 processor core, which is out of 10 to 20% of the single server capacity. And the typical time spent in the whole process is about an average 2.5 minutes, which is something like we can say 4 triggers can be processed in each expected trigger time. For example, 10 minutes, we expect 1. So that's why actually a real-time requirement of the spotlight is a 1 trigger for this expected, 1 trigger about 10 minutes. All right, so I'll leave it to this summary. I'm sorry, it was too fast, I guess.
All right, thanks a lot, Sanjay. Questions?
Hello, thank you for the nice here.
Yeah.
Hello, thank you for the nice talk. I just wanted to request, can you please repeat again what you did with these 2 images? I didn't understand.
This one.
What's the difference between the 2?
Okay, so this is actually originally what data we get it here. This time, although of course when the trigger is generated, we record the data for the starting time of the trigger to the end of time, plus some extra data around it for padding. And the trigger time, the burst time actually comes along with the detection pipeline. From that time onwards, we know the DM of the burst. This is my starting time. This is my dispersion curve from the starting time of the burst. Suppose if you know the pulsar, I do not have pulsars here. If this is actually pulsar, what pulsar would look like something. And this will disperse or something along this dispersion line. My last pulse will appear somewhere here. So what I do, I start from somewhere here and end up to here, this point. This is my data recorded, okay? And then I model, given that the DM, I can put a curve here and this curve, there are two starting points. If I trace this curve, this will start here somewhere. And this point will end it here. Okay. So I make this marker and only the visibility within these two curves, I send it for imaging. If I send anything else, that will make all my scale available for imaging. But now this is the strongest source or strongest pulse that will dominate field of view, so that you won't see anything else in the image rather than this. Of course, if this were very weak burst and there is a strong source in the field of view, that can also be visible. But most of the time, this is the ruling. This is dominating in the field. And second plot is actually, if you look at this stage, this one, these are actually band pass. They're actually normalized here, so that actually your pulse appearing here is actually completely overscaled in all frequency channel. That's called a band pass calibration or amplitude scaling.
Right. Time for one more question. Don't see any hands. All right. If not, let's thank Sanjay again.